Hello, and thank you for joining today's webinar about EMI 101, in which I will focus on FERRITES. My name is Oscar Gonzalez with Würth Electronics, and my intention today is to go over the basics of EMC, also understand some important characteristics about FERRITES and how to choose and implement one in your projects. At the end of this presentation, you will be able to ask any questions you may have about the topics exposed in this presentation. So let's go ahead. So the purpose of this webinar is to give you an overview of what EMC is and how it may concern you and your company. Once we understand what EMC is, we will then talk about chip-bit ferrites and understanding the information shown in their datasheets. Next, we move on to defining losses and the details of insertion loss calculation. And finally, we will finish up with a discussion about clamp-on ferrites. So first of all, we need to identify the differences between EMI and EMC. So every electronic device emits EMI or electromagnetic interference. How that affects your device and other electronic devices is where EMC comes in. The EMC, or electromagnetic compatibility, is concerned with how well your product interacts with other products within its environment. So as you can see from the picture, the world is a busy place in this field with EMI. Your job here is to make sure that your device does not cause any unintentional failures to other devices, while at the same time protecting your device from the EMI caused by others. So in short, in order to be electromagnetically compatible, you need to prevent emissions and have high immunity. So keep this statement in mind as we move forward in this presentation. There are many types of electronic devices in the world that provide many types of different applications. The level of the products goes from very simple to very complicated. And with that being said, the impact of a failure of one of these devices may be harmless or may be life-threatening. So therefore, there are many regulations for EMC to ensure the safety of electronic devices and make sure there aren't any unintentional failures caused by EMI. IEC is a worldwide standard and EN is an European standard. I am sure that you have already heard about them before, so we won't get into the details of each standard today, but I just wanted to show you that there are very specific regulations for several industries. For example, here we have medical equipment, we have industrial equipment, information technologies, white goods, and so on. So it is very important that you are aware of what regulations your product needs to meet in order to bring your product to the market. It is not up to the manufacturers of EMC components, such as Wurth or EMC labs, to tell you what standards you need to meet. So you will need to know this by yourself when getting your product tested at the EMC lab for certification. The EMC lab may be able to point you in the right direction, but at the end of the day, it is your responsibility. So there are a few different types of EMI. Understanding each one of these will help you identify what might cause any EMI issues that you will encounter in your project. So first of all, we have conductive coupling, which is a physical coupling path that is formed by a direct contact. An easy example is a cable, or it may be a wire, but keep in mind that it can also happen with any trace of on a PCB or even a metal enclosure. Then we have capacitive coupling, which is specific to an electric field. This occurs when a varying electrical field exists between two adjacent conductors. So for instance, when you have two plates with a potential difference separated by any space, Essentially, what you have is a capacitor. Then we have inductive coupling, which is specific to a magnetic field. This occurs when you have a varying magnetic field between two parallel conductors. This causes parasitic induced voltages. And last but not least, we have radiative coupling, which occurs over the air. So every trace on a PCB is a potential antenna, and therefore a potential coupling path. Typically in high voltage applications, capacitive coupling will dominate, whereas in high current applications, the inductive coupling will dominate. And now I want to show you an example of what not being protected against EMI causes in your products. So here we are using an old picture as an easy example of what EMI looks like. So on the left, you see a picture as taken from an old television. The picture looks good and it does not show any noise problems. But because this old television was not designed with EMI in mind, it is susceptible to failures caused by the environment that it is operating in. So the picture on the right shows the result of the interference. To put this slide into a real-life scenario, you have to envision yourself watching TV. While watching your show, someone has decided to vacuum the living room, for example. So the result of the EMI emitted by the vacuum affects the circuitry of the television, resulting on the distorted screen that you see on the right. So luckily, standards have now been put into place to prevent this situation. As stated previously, in order to be electromagnetically compatible, you need to prevent emissions and have high immunity. Emission is concerned with the EMI leaving your device, and immunity is concerned with EMI entering your device. So there are also two types of each of us. We have conducted and we have radiated. So conducted is a direct connection like a wire or a cable, whereas radiated means through the air, which is in an electromagnetic field near to your device that may affect it. So just to be clear on the types of interferences, a conducted emission is EMI leaving your device through a direct connection. A radiated emission is EMI leaving your device as radiation through the air. The conducted susceptibility makes reference to the immunity of your device to not allow EMI to enter through a direct connection. And last but not least, the radiated susceptibility means the immunity of your device to not allow EMI to get in as radiation through the air, pretty much. So as mentioned previously, there are a number of EMC regulations out there. Two that we run into quite often are CISPR 22 and FCC 15. I will not get in a detailed explanation about this. This is just a quick overview of each one. So CISPR 22 is a standard applicable to the European community. It tests for conducted noise at 150 kilohertz to 30 megahertz, and it tests for radiated noise at 30 megahertz to 6 gigahertz. On the other hand, we have the FCC 15, which is a standard applicable to USA. It tests for conducted noise at 450 kilohertz to 30 megahertz, and it also tests for radiated noise at 30 megahertz to either 40 gigahertz or the fifth harmonic of the highest frequency of your circuit. So anything above 10 megahertz is where you should start considering that there is a common mode noise issue. The chances are higher that it is common mode noise above 10 megahertz, but of course this is not a guarantee. It is possible to have differential noise above 10 megahertz, but this does not happen very often. So to dig into CISPR 22 and the FCC 15 a little further, this slide shows the conducted and radiated tests performed at the same frequencies. but breaks it down into Class A and Class B. Class A is for commercial, industrial, and business environment equipment, and the Class B is for residential environment equipment. The tests for the Class A are more stringent because of the environments they will be operating in. So in terms of similarities, the conducted and radiated emissions limits specified in the CISPR 22 and FCC 15 are close to each other. So in this way, it is possible to meet both the standards easily for the certification process. So now let's talk about the details of chip-bit ferrites and how to pick out the important specifications from the datasheets. So we will talk about how what they are, how they work, picking out the right part from the datasheets, and how to use them. So a chip-bit ferrite is nothing more than an inductor, and it is used to remove unwanted noise at high frequencies on supply voltage lines, also ground planes and data signals. So if you remember the law of conservation of energy, you remember that energy cannot be created nor destroyed. It can only be converted. So that is exactly what a chip-bit ferrite is doing in this application. It is transforming unwanted signal energy into thermal energy. And in other words, it is converting the unwanted signal, aka the noise of your circuit, into heat. So in order to maximize impedance of an unwanted signal, you need to choose the appropriate material that has the best characteristics to absorb the specific frequency that you're trying to attenuate. This material must be non-conductive to ensure it does not short to the core. All of Wurth's chip-bit ferrites use nickel zinc because it is a non-conductive material. So what you end up with is a frequency-dependent resistor. The picture on the right shows you the parasitic of a chip-bit ferrite. Here we need to always be cautious of this because a chip-bit ferrite has inductance, it has capacitance, and it also has resistance. So we will discuss this in more detail later in the presentation. So this slide shows you an X-ray view of a chip-bit ferrite. Keep in mind that the windings are not insulated and the core is non-conductive. So as you can see, the winding of the high current chip-bit ferrite needs to be thicker in order to handle higher currents, and therefore is wound horizontally, just to have more space for the large winding. The high frequency chip-bit ferrite needs to maximize the number of windings, and therefore it utilizes the space it has by being wound vertically. So due to the reduction of the effective area of the conductor, less current can be carried by the high frequency chip-bit ferrite in comparison to the high current chip-bit ferrites. The main point that I'm trying to show you here is how these two types of chip-bit ferrites are manufactured differently just to provide their intended end use. So if we base on physics, we can understand how inductive reactance works. So if we base this explanation on the picture shown at the right of this slide, we need to identify the primary current flowing through the inductor, which is marked with a red arrow. Also the magnetic field generated around the turns of the inductor, colored in blue, and the resulting induced current from the changing magnetic field, colored in green. So inductive reactance is the result of a primary current fighting with the induced current in a helix type of winding. This phenomenon happens due to Lenz's law. This formula, you can actually see it at the bottom left of this slide. And as you can see, the inductive reactance, or XL, is a function of frequency and inductance. So this is just a simple explanation of how inductive reactance works in an inductor. And so as mentioned previously, A chip bit ferrite has inductance, it has resistance, and it has capacitance. You can see these characteristics shown in the blue, green, and yellow areas of the graph on the right of this slide. So this is what you see in a typical datasheet of a chip bit ferrite. I would like to remark three curves that are shown here. So first we have C, which is the impedance. This is the main curve of the graph. You also have XL, which is the inductive reactance. This is colored in the graph as a blue dotted line. And you also have the resistivity, which is not the DCR. This is just the resistivity of the part. So this is colored as a red dotted line in the graph. So now the crossover frequency is where the inductive reactance and the resistivity meet, shown here as the red and blue dotted lines, of course. So below the crossover frequency, the inductive reactance is higher than the resistivity, and therefore the part is better used as an inductor for energy storage purposes. Above the crossover frequency, you see more resistivity, and therefore this part is better used as a filter at those frequencies, up to the self-resonant frequency or the SRF of the part. Then we have the self-resonant frequency, which is the highest point where there is no inductive reactance and your impedance and resistivity are at its highest point. The main purpose of a chip bit ferrite is to block unwanted AC noise frequency. So anything over the SRF will become capacitive, which passes AC and blocks DC. So therefore, if you need a filter, you do not want to be in the capacitive region of the chip bit ferrite. So after the self-resonant frequency, this device will not work for our circuit. To block noise effectively, just make sure that you choose a chip bit ferrite with a high impedance in the range of frequency where the noise is located, so it is attenuated properly and does not affect your useful signal. As with other magnetic technologies, it is very important when choosing a chip bit ferrite to pay close attention to heat. As mentioned previously, we are converting an electrical energy to a thermal energy and dissipating it as heat from our circuit. So there will be a temperature rise of the part, and we must also be aware of the ambient temperature in which the part will be used. So sometimes it will be necessary to derate the current because the core is temperature sensitive. For commercial grade products, the core material we use has a maximum operating temperature of 125 degrees Celsius. Because above 125 degrees Celsius, we come close to the Curie temperature and the permeability drops down to 1. So the Curie temperature is where the material starts to lose its magnetic properties. So we must take care of the temperature of operation of our component as well as the current flowing through it. Here is an example of a product that has an ambient temperature above 85 degrees Celsius. So we specify on our datasheets a 40 degrees temperature rise above ambient temperature when used at 5 amps. So remember that a part used in an 85 degree ambient temperature with a 40 degrees temperature rise will result in a maximum operating temperature of 125 degrees Celsius. And we cannot exceed the recommended maximum operating temperature, so this is our limit of operation. In this case, we have an ambient temperature of 105 degrees Celsius. So when we add in the 40 degrees temperature rise, we will be exceeding the 125 degrees maximum operating temperature, and therefore we must derate the current of the part. According to the graph shown on the right, we see that at 105 degrees Celsius, we must derate the current by 50%. At 2.5 amps, you get a 20 degrees temperature rise above the ambient temperature. So the result of an ambient temperature of 105 degrees Celsius and a 20 degrees Celsius temperature rise puts us safely at the 125 degrees Celsius maximum operating temperature. We specify our chip bit ferrites with zero bias. This is something important to keep in mind. So therefore, we only show you the impedance that you will get with no current flowing through the part. So for example, this slide shows 330 ohms of impedance at 0 amps. So if you were to add current flowing through the part, you will be saturating the core. If you saturate the core, the impedance drops and the frequency shifts. We do have actually LTO spice models, but only for our high current chip bit ferrites, so you can run your simulations. So how you need to choose a chip bit ferrite? Well, the answer is pretty much that it depends. So based on your application, you need to take into consideration the frequency range of the noise, also the source of the noise, the amount of attenuation needed, the environmental and electrical parameters of the circuit, and as with everything else, space and cost. So it becomes a trade-off between all of these considerations based on the priorities of your situation. Next, we will talk about losses. And the reality of life is that in electronics, everything has losses. So the key is to understand what your losses are and control them as best as you can. So regarding the core's properties, we need to pay close attention to the permeability specifications just to make sure that it will fit in the application. So every core manufacturer specifies mu prime and mu double prime. Mu prime is the inductive reactance in the frequency range where it is best used as an inductor, and the mu double prime is the resistivity where the part is best used as a filter because this determines the losses of the core, meaning that it will convert the noise into heat. We can actually deduct the role of each coefficient of the complex permeability based on the impedance formula shown on this screen. We see that the inductive reactance is dependent on mu prime, and the resistivity is dependent on mu double prime. So the same component can be used for either filtering or for inductance, depending on the frequency that it is used. Just so you know, you can refer back to the crossover frequency discussed earlier in order to identify these frequencies. So focusing on the graph shown on this slide, this core material could be used well for an inductor if the frequency of operation is between 1 and 3 megahertz tops. So after 3 megahertz, the mu double prime is very high and the material will have high losses, meaning that it can convert electromagnetic energy into heat. If we identify noise with a frequency higher than 3 megahertz, we could use this material to attenuate it. Now, different materials have a different frequency response. So here we are providing you a guideline for what materials are best suited for what frequencies. So keep in mind this just a guideline based on typical situations. So like with anything else, there are always exceptions, of course. So there are 3 typical materials that we can find for these applications. First of all, we have iron powder, which is the yellow portion of this graph. This is typically used for lower frequencies for noise attenuation because it has the highest core losses at frequencies between 200 kilohertz to 4 megahertz. We also have manganese zinc, which is the red portion of this graph, and it is typically used for frequencies between 3 megahertz and 60 megahertz. And last but not least, we have a nickel zinc, which is the purple portion of this graph. This is used at frequencies of 20 megahertz to 2 gigahertz, because it is very resistive at higher frequencies. And so now, if you enjoy performing long mathematical equations, you are going to enjoy this portion of the presentation. But if you do not enjoy performing long mathematical equations, you are going to enjoy this portion of the presentation even more, as I am going to share with you right now some of the tools that we have to make your life easier. So now let's talk about how to do insertion loss calculations and some tips and tricks that you can get to do this easily. So there are a lot of long and difficult mathematical equations to determine how much impedance you need for a component to be within a specific certification for attenuation. And that is represented by the equations here for system attenuation and for impedance. So because of the parasitic properties of the component, it becomes a very difficult and time-consuming mathematical challenge. I will not do a detailed explanation of both formulas, but you can look at them on this slide so you get an idea of the parameters that we need to get into consideration when calculating the impedance needed at a specific frequency to get the attenuation that we are looking for. So the previous image just showed the parameters that we need to consider when doing an insertion loss calculation. This picture right here is a simplified representation of your design. So you have a source and you have a sink. The interaction of your source and sink will cause some noise. So depending on the amount of noise created and at what frequency, this will influence the type of filter that you need. If you have the time and are up to the mathematical challenge, feel free to use the previous equations, or you can use this nomogram you see here. As you can see from the legend below, the typical applications are listed. So we have ground planes, we have supply voltage lines, we have data signal lines, clock, video, USB, and also long data signal cables. The assumed practical system impedance of these applications is shown to the left. So keep in mind that these system impedances values are just approximations and not exact representations for all the applications. But as you will see, for our purposes, the approximation works just fine. And most important, it saves us a lot of time. And most importantly, actually saves us from having to do the painful mathematical equations. So how do you know what type of application to use? Well, you know your board already. You know where the data signal lines are on your board, you know where the ground planes are, and you know where the supply voltage lines are. So again, in this picture, you can see approximated values of impedance for each stage of your circuit. So the ground planes are identified with black arrows, and the supply voltage lines, the supply voltage line is pointed with a red arrow, and you can see the data signal lines pointed with a blue arrow. So every PCB has system impedances associated to it, and this is what CA and CV from the insertion loss calculation equations refer to. Either a source impedance, which is where the interference or emission is coming from, and the load impedance, CV, which is where the interference or emission is traveling to. So what do we mean by system impedances? Well, pretty much the ground plane on a PCB is a large expanse of copper material, and in electrical terms should be 0 volts. To achieve these 0 volts, we need as low resistance as possible, and typically this is 1 to 2 ohms. Next, we have power ports and power lines on the PCB. Once again, we require this to have a low impedance, otherwise we will not have an efficient way of transferring our intended energy around the PCB. And this is why these are typically 10 to 20 ohms. Any external signal cables that connect to your device under tests are likely to have defined impedances. in this case, we have a LAN or Ethernet port. This has an impedance of about 100 ohms. Typically, these lines have an impedance higher than 90 ohms. So 10 ohms is a really cool approximation. So for this example, we know that we need 12 dB of attenuation at 125 megahertz. We know that the application is a power cable and has we can double check our work with the equation for attenuation below. We just substitute the filter impedance for its actual value, which is 59.6 ohms. And we can confirm that the resulting attenuation is 11.99 dB, the value of attenuation that we need for our power cable at 125 megahertz. So pretty much what we did is that first we just calculated the impedance needed for the attenuation that we need, and then we just confirmed that this impedance value is actually correct. So if you have the same scenario, but this time you use a nomogram, you will find that you quickly come to the same conclusion without doing any mathematical equation. So keep in mind that the frequency is built into the impedance, and therefore you do not have to use the frequency when using a nomogram. You know you need 12 dB of attenuation. You know that it is a power cable with an impedance of 10 ohms. So therefore, you use the solid black line for the supply voltage applications in the nomogram. Follow it until it reaches 12 dB, and you find your result of a 60 ohms impedance requirement. As you can tell, we got pretty much the same result that we got using the mathematical equations, but this way is easier and faster. So just so you know, the nomograms are provided in our catalog and on our website, so you can use them to do the quick estimations for the component you need to pick for your application. So now let's see how our clamp-on ferrites are able to help you with the noise that you might find in your projects. We make our clamp-on ferrites with two different materials. We have a manganese zinc and we have a nickel zinc. This slide provides pretty much a guideline for which material to use depending on which situation you are in. So as I have stated previously, there are always exceptions, but this is what we find to be typical. So to choose the right material, you need to identify first the type of noise that you have in your system. Either it is conducted or it is radiated. So once you identify the type of noise, you can choose the clamp-on ferrite material that you need based on the graph that we have on this slide. So you may use a nickel zinc in situations where you have either conducted or radiated noise. And you can use manganese zinc clamp-on ferrites for pretty much conducted noise. So to choose the right EMC component, it is very important to identify the noise that you have in your system. So first you need to question if you are dealing with common mode noise or differential mode noise. So here's a quick trick to get you heading in the right direction. It is not 100% accurate, but will help you start the process of elimination. So similar to a doctor prescribing antibiotics without knowing if you have a bacterial infection or a virus, he prescribes the antibiotics knowing that if it is a bacterial infection, the medication will work and the problem is solved. If the medication does not work, then at least he knows he's dealing with a virus. So in our case, if you simply apply a clamp-on ferrite onto the cable, both lines, VCC and ground, if the noise is reduced or the immunity is increased, then you know that you're experiencing a common mode problem. But if there is no effect, if there is no attenuation at all, then you have a differential mode problem. So therefore, at the Wurth level, if you have a common mode problem, you could use a common mode choke. If it is a differential mode problem, then you could use a cheap bit ferrite. So here's a visual representation of how a common mode choke works. As you can see in this animation, the red arrow is the differential signal going in, which is the useful signal of your circuit. It creates a magnetic field inside the core going in one direction according to the right-hand rule. And then the differential signal has to go back to the source, which creates another magnetic field according to the right-hand rule. These two signals cancel each other out, so the animated crash is giving you a visual representation of this cancellation. So now, if we talk about common mode noise, common mode signals, we need to understand that both signals are flowing in the same direction, just as we can see in the blue arrows from this image. The common mode noise will create a magnetic flux inside the core that are in the same direction as shown here by the blue arrows. So the core will react to that frequency and convert it into heat. So this is represented by the mushroom cloud in the middle of the core. This fact makes it important that you choose the right core for the specific frequency that you're working with. So, in conclusion, because of the winding structure inside the part, we are not influencing the signal, and therefore, if we choose the correct core based on its complex permeability, and specifically a high resistive portion at the frequencies of the noise, we will get a high attenuation of the noise that we have in our circuit. Now, something to keep in mind when using a common mode filter is that there will be a differential impedance that could attenuate your signal. As shown in the graph above, the blue line represents the common mode impedance, and the red dotted line shows the differential impedance. If your useful signal is at 100 megahertz, for example, and you're using this common mode choke for your solution, you will be unintentionally attenuating your signal. It is important to take a look at both impedances just to make sure that it is good to attenuate the noise and not affect your useful signal. So the next slide will show you a specific example. The blue line right here represents your common mode impedance, and the red dotted line once again shows your differential mode impedance. Your useful signal is the thick black line at 4 megahertz that you can see on the graph. So as you can see, you're making a good use of the common mode choke because it has a high common mode impedance at 4 megahertz and low differential mode impedance. Therefore, the impact on your useful signal is kept to a minimum. The impedance and the upcoming attenuation on your signal is not significant. Our datasheets will show you both the common mode impedance and the differential mode impedance for that part, so you can be aware of the effects that you can expect on your signal. So there are two types of windings in our common mode chokes. We have sectional windings and we have bifilar winding. The sectional winding components are mostly used for power supply applications, but can also be used as an inductor to attenuate differential mode noise. The sectional components have a higher leakage inductance and therefore, just as we discussed before, they attenuate differential mode noise as well as the common mode noise. So bifilar winding parts are typically used for signal lines because we don't want to attenuate the differential mode signal, meaning your useful signal. So there is a lower leakage inductance that is utilized for filtering noise on a signal. So it is important to know that where the differential mode impedance is and be aware of your differential mode signal. Common mode noise can be solved with a sectional or a bifilar winding part. And the way that it attenuates the noise is very similar. In contrast, there is a big difference if you're using a sectional or a bifilar part to attenuate differential mode noise. You can see these differences as shown with the red and blue lines in this graph. So the sectional winding provides a higher differential mode impedance at any frequency in comparison to the bifilar winding. That's the reason why it is mostly used in power supplies, because we don't worry about any differential mode signal. However, the bifilar winding is good for data lines because we care about our differential mode signal, which should not be attenuated, and its low differential mode impedance helps to keep this attenuation at its minimum. Now, we will take what we just learned about common mode chokes and we will apply it to clamp-on ferrites. So the clamp-on ferrites are typically used as common mode filters. A single cable goes through the ferrite, but the cable includes two wires. It comes with VCC and with ground. So you can also use a clamp-on ferrite as a differential mode filter. But now you must separate your wires in the cable so that you have a single wire going through the ferrite. So the type of clamp-on ferrite you choose will depend upon the intended use that you want to give it. So our clamp-on ferrites are made from two materials. We have manganese zinc and we have a nickel zinc. The blue line right here represents the nickel zinc parts. This is the impedance curve that we can get from this clamp-on ferrite with only one turn. As we can notice, its impedance is actually not very high. So, by adding multiple turns through the ferrite, you are increasing the impedance, but you're shifting the frequency range because you're adding capacitance. So this second curve shows impedance you will get if you do two turns through the clamp-on ferrite. This third curve shows impedance with three turns. So as you can notice, a higher impedance but shifted frequency range. The red line right here represents the same example with the manganese zinc. So here we can see the impedance with only one turn. If we add another turn, we can notice that impedance increases, but the frequency is not shifted drastically. So that is because the manganese zinc is a much narrower bandwidth material. And then now we have three turns through the manganese zinc clamp-on ferrite. Notice that as you add turns with a manganese zinc product, you increase impedance, but the frequency does not shift drastically. So depending on the frequency and the impedance that you need for your application, you will need to choose either a manganese zinc ferrite or a nickel zinc ferrite. Now this slide shows three different types of clamp-on ferrites that we offer. First, we have the FIX-LFS or low frequency suppression, which is made of manganese zinc and therefore used for low frequency noise attenuation. We also have the Star Tech, the Star Ring, and the Star Fix, which are made of nickel zinc to attenuate higher frequency noise. Last but not least, the Star Gap. This is a clamp-on ferrite aimed at the noise above 100 MHz up to 2.5 GHz. So once again, it all depends on the range of frequency where you need to attenuate the noise. So hopefully by this point of the presentation, you have gained an appreciation of designing your products with EMI in mind. So if you do not, well, you can find yourself spending thousands of dollars per visit to the EMC lab trying to fix your problem. Or it can get even worse. I mean, you can find yourself being fined in amounts in the hundreds of thousands of dollars because you're not complying to the EMC regulations required by your industry. So in summary, using relatively inexpensive EMC components at the beginning of your design can show you a big cost savings by the time you ultimately get your product to production. This is a bonus slide that I would like to share to you. We have a lot of tools on our website to help you choose the proper component for your application, as well as direct salespeople and application engineers located all over the world that will be willing to come visit you in person to get the best solution for your EMC problem. I highly recommend you to use our software, Red Expert, to simulate the needs of your system and get the best options available for your design. We have sections dedicated to chip-bit ferrites, also common mode chokes for mains power lines and for data lines. We also have a simulator for cable ferrites and more. So feel free to try it and enjoy the benefits that it can get you by selecting a suitable component for your application quickly. So thank you very much for your time today, and please feel free to contact us. At this time, I am willing to take a few questions, and will answer them to my best of my ability. So please feel free to enter your questions using the chat button. Okay, so here we have a question. Shouldn't a ferrite on 50 ohm data line have a 50 ohm impedance in order to match the line impedance? Well, in this case, you have already an impedance of 50 ohms. And the 50 ohms, you're having some noise in your line. So what you need to do, or what you need to try to do, is to have a high impedance only at the frequency where your noise is located. Let's say that this noise is located at 100 megahertz. You will need then to take a look and see any ferrite, any chip-bit ferrite, for example, with a higher impedance than 50 ohms. So you can increase the impedance at the frequency range where your noise is located. Of course, we need to double check the matching of impedances, but for this specific application, which is attenuating noise, you will need to choose a chip-bit ferrite with a higher impedance than the one that is driving your line to attenuate that noise. I hope I answered your question. Also, we have, is this presentation going to be available after the webinar? Of course, it was mentioned at the beginning of the presentation. This webinar will be available as a recording within 1 week approximately. So yes, you will have the chance to watch it once again. One more question. Okay, so here we have one. What material are the low frequency chip ferrites made from? So we have actually many materials. Some of them, well, the ones designed for a low frequency range are actually manganese zinc. Of course, we have some other mixtures, but pretty much all of them are made of manganese zinc. We also have iron powder that is actually one that is used for even lower frequency ranges than the ones designed with manganese zinc. So yeah, we have actually many materials available for chip-bit ferrites. So if you have noise at a low frequency range, please feel free to use Red Expert. You can actually just simulate your system and it will recommend you some parts, or you can also consult an application engineer from Wurth Electronics so you can get your question answered. Let's just take a look at some other questions. Does Word have simulation files for the chip bit FERRITES? Yes, we actually have simulation files available on our webpage. If you go to our webpage, which is www.we-online.com, you will get in the online catalog. All you need to do is to first locate the ferrite that you need. And once you locate it, in the same page where you found it, there will be a column named downloads. In that column, you're gonna see many labels. For example, the label LT is the label assigned to the LT Spice model. We also have models for Eagle, also for we have for Altium as well. So yes, we do have simulation files available on our webpage. We also have STP files and 3D PDF files, so you can have a 3D visualization of the part. Also, the STP may be used to design a 3D model of your PCB, for example. So yes, we can offer you many models for your designs and for your prototypes. Let's see what other questions we have right here. Okay, most of the information was concerning about high frequencies. What if noise is at lower frequencies? Are FERRITES not appropriate for noise under 100 kilohertz? Definitely. I mean, we have in this presentation focused on high frequency pretty much, but of course we also do have chip bit FERRITES designed for low frequencies. It will be a matter of just taking a look exactly what chip bit ferrite may be good for your application. But yeah, of course, we do have chip bit ferrites, or even in this kind of situations, if you have noise at low frequencies, you may also want to use an inductor if it has a high impedance at the frequency range that where you have the noise. So yeah, it will be a matter of just double checking if we have a chip bit ferrite for the frequency range where your noise is located, so we can see if we can use a chip bit ferrite or probably an inductor as a solution. Let's just double check. Okay, how to source a chip bit ferrite from Wurth? Well, pretty much, I would say that we have three options. The first one is that you can contact your direct Wurth representative. They can work with you directly, so they can source for you the right chip bit ferrite. If you like more the self-service options, you would like to try two of them, which the first one is the online catalog. There you can see all the series that we have available for chip bit ferrites, as well as for clamp-on ferrites and common mode chokes. But it might take you a little bit of time because you will need to take a look at each series. So the best one, the one that I recommend the most, is using RedExpert. This is pretty much an online tool designed for filtering components. So you can apply your filters. For example, for chip bit ferrites, you can filter based on the DCR of the part, also the current capability. You can even filter the size if you have a size constraint in your PCB. So yes, you may use RedExpert, you can do the simulation, you can source the right chip bit ferrite for your application easily and quickly using that software. So, okay, that's all from my part today. I really want to say thank you for joining today to this webinar. If there are more questions, of course, I will go ahead and receive them and I will answer them via email. So that's all for today. And once again, thanks a lot for taking your time to assist to this webinar. So please stay safe, stay home, and stay healthy.